right? And within that, we started with the capacitive touch screen and then went on creating a model for that, a circuit model for that, and then moved on to developing a firmware for measuring any capacitance based changes that might occur. So we were sort of halfway done through that. We did create one piece of code that is capable of registering the touch, right? We went through the touch sensing cycle and so on. So we are going to look at continue from on that end, and then we'll try our best to wrap up on the touch sensing side, so that after the break is over, we can resume over other things, for example, localization and so on, right? So this was the synopsis of what we discussed in the last class, and we tried to implement this thing. So this is one sensing cycle for capacitive touch that consisted of two distinct parts. One was how we were discharging the sensing pin, and after that we make the reference pin high and wait for the amount of time till the sensing pin reaches a certain threshold voltage, so that it becomes digital 1, right? Once we keep on reading this pin sense whether it has turned on or not, that basically becomes digital 1 at a certain point in time, and we put some extra amount of time so that since it was not exactly charged, or like the voltage of that particular pin was not exactly 5 volts, so we put some more time for charging that particular pin. So it was sort of discharging and charging a particular pin in our sensing circuit, right? So this was charging of the pin or pulling up the voltage of that, right? So this was done using the reference pin, or there are many terminologies. So in some of the literature, if you look it up, right, you'll see this is also known as a receiver, right? And this one could be a sender or a transmitter, right? So there are many terminologies around this, and then I'm going to share a research paper which is pretty much of a survey on this particular topic. So anybody who is interested about knowing more about this field, or how if you have an active interest about human computer interface interaction, how these new interfaces are being developed just using touch as a modality, you are welcome to look into those papers. Okay, and they will have a pretty comprehensive distribution of all the different types of like all the different types of techniques that are actually used. So what I am teaching you in the class is sort of a very generic and a high level overview, but this will have very lots of internal details, how all these individual things are implemented, how the sensitivity is increased, and so on. So we saw all these two phases, right? Discharging and charging and so on. So this was our pseudo code for the raw sensing cycle for our firmware implementation. It started with a discharge, and then it was a sensing part where we calculated the value of delta. We kept on accumulating or adding the value of the delta till that particular pin becomes digital 1. Right? Before that, till that particular condition is reached, we keep on increasing the value of delta. Okay, and then after this is over, there is one more charging cycle, and we return the value of delta, right? And we saw one variant of this, right? If we just call the sensing cycle function from the loop, right, it was causing some misdetection, right? We were not able to register all the touches, and then we tried to make this program a little better. We wanted to include a loop, right? And within that loop, we were accumulating the value of delta, right? By the way, there was one problem that I had in the last day's classes code. So I missed this and, right? So otherwise it will be syntactically a problem. I did not update in the video, but the classes slides are updated. So just make sure you, because it's a pointer, so it's an address of the delta, right? The value delta. Okay, and we were writing out this particular set of values to the serial port. Okay, so what we were doing is trying to accumulate these values together, and we also saw the effect of this, right? There were like we could register most of the touches, but there is this noise that is present, and we don't know what we are missing out. So sometimes there was a problem with the response, but it has definitely improved compared to what we had in the first place, where we did not use a loop, right? So there were these two kind of scenarios. One was using the loop, and the other was not using the loop, where we had missing samples, so we could not register all the touches, as we saw in the previous classes demo. And for that, we wanted to have a robust filtering mechanism, which is going to help us register the touches, and at the same time, it is going to be interactive. So there should not be any latency, or there should not be any missed detection, right? So these kind of things has to be kept in mind in our filtering algorithm, and we might have to rethink the sensing metric. What we are right now plotting was the value of delta, right? And as you could understand this, if we have to use a threshold, right, when we develop the final code based on what object is touching the circuit, or what material is that particular object made of, those will influence, as we will also see later, those will influence the value of capacitance that is brought into the circuit, and that is also going to influence the value of delta, right? So if we just track based on the raw value of delta, that might not be a robust sensing metric, right? It does not, because once you, how do you detect touch, right? Once you cross a certain threshold value of delta, you will probably declare that a touch has been detected, right? If it is under a threshold, you will say that there was no touch, right? So that is how a standard event detection will be implemented. So in this case, we are detecting a touch event. So just calibrating the delta value, right, will not make much sense, because these values will change from touch to touch, person to person, object to object, right? So the value, we cannot just simply base the threshold on that particular value. So we have to do something better, right? Also, you could see that like there are certain flips and noises that are present here on, and you can see there is something, some kind of a saturation, or some kind of a DC level you also see, right, in different parts of the plot, right? It might not be a unique problem of this code, but it could be a problem with the particular set of circuitry I had, right? You have to choose what object you are using to touch, who is touching the a particular circuit, and so on, right? What objects you have in your hand, so everything matters, right? So you can try to recreate something like this, and you will see some version of this problem that is happening, and that is sort of inspiring us, right, or to make some other calculation or improve the sensing metric. So one idea, of course, would be a window-based mechanism, right? As we all understand that it's better to operate on a certain window, because all the fluctuations will be local to a certain small time period, and those values, as you have also seen in case of the pulse oximeter, we were looking through the values of the voltage in the IR sensor, and those values will keep on changing with time. So it's better to concentrate on a small time window, and within that time window, we are going to look at how the statistics of those values change, right, and have a better calibration for the making the event detection much more efficient. Okay, so again, this will be a sliding window, as many of you have already implemented such kind of techniques in case of heartbeat detection, right? And the other thing, just a minute, I'll take a small pause. This is continuous sound. Is there a hum that you can see? You can. Do you have some kind of an hum on your side, guys? Or is it
Yes,
on?
sir. Yes, sir.
Okay,
Like
so
nighttime noise. Yes, sir.
yeah, can you keep that mute? Can you keep your microphone muted? Okay. Okay, thank you. So we were talking about this windowing mechanism, right? That we will require for filtering out the noise, and we want to keep the statistics local to a smaller time window. Okay, and what we want to do here is this is a heuristic, right? This is one idea which is definitely going to make the sensing work better, right? But this is in no way kind of an optimal solution, right? This is just one idea which is going to take a better step than what we had, right? And if you want to develop more sort of sensitive algorithms that will be kind of recover your touch based on even a lot of noise that is being present in the system, you have to do something more sophisticated. So here is the idea. So we'll do the cumulative sum as we were doing, right? So we were adding the values of delta for every sensing cycle, and in this case for 10 sensing cycles we are having a cumulative sum. Okay, this is kind of addition of the individual deltas over the windows. So these windows could be depending on how you choose, right? It could be overlapping or non-overlapping. It could be sort of you what is the choice of your window, right? So for every sensing cycle that happens within the window, you are basically having a cumulative sum of the deltas. So every sensing cycle will have one value of delta. Okay, so you'll have here 10 deltas. Okay, so and those addition of the 10 deltas is what you are getting. So, and the other thing that we are also trying to track is the historically available value of the delta list, right? Within a window, right? Previous windows you have also figured out similar values of delta, and what we are trying to see is that what was the value of delta list that has been encountered within a like within some short history, right? It is like that history is also variable, right? How much history you want to consider. But we are what you can understand that we are trying to do some sort of a DC cancellation, right? Earlier, if we know that the DC list is something like this, right? What was the earlier known available value of this delta list, and what is the current value of the delta? We are trying to take a difference of these two, right? Instead of reporting the raw value of delta, so this is, I would say, the raw value of delta, right? Instead of just reporting this, because this is a function of as I told you earlier, a function of the object that is touching or the particular context in a particular scenario, what is the circuit and so on, right? So instead of depending on the raw value of delta, we are trying to sort of self calibrate the system. We are not using this raw value. Instead of that, we are also keeping track of the raw delta list. Okay, and this could be recalibrated. The delta list value could be recalibrated every k seconds. So for k seconds we are trying to keep a history, and within that time whatever is the value of delta list that will be subtracted from delta. So what we are reporting is delta minus delta list. Okay, so if you do that, we are sort of removing some dependency on the type of object, because as I told you, we were not kind of interested in measuring the exact value of capacitance. Okay, although this difference is also going to reflect some of it, right? But this is going to take away the problem that we saw earlier. Okay, or the problem we see in the current plot. So we will see how this heuristic implementation looks like. So instead of reporting the value of delta and plotting that, what we are going to do now is keep track of this delta minus delta list. Okay, so here we were already doing something like this, right? So for how many samples you were using this particular sense one cycle code we are calling, and let's say this delta is global, right? So instead of returning the value of delta from the sense one cycle function, it is going to keep on adding it up, right? So this delta is initiated to 0, and after that for how many samples you want to continue, maybe 10 times or 20 times or 30 times. We are just going to keep on accumulating the value of delta, and after that there could be a recalibration timeout, right? If we are continuously seeing that what is the like trying to keep track of the history, right? So if this timeout occurs, so then we recalibrate the value of delta. So this is like we keep track of the delta list, and depending on how much time has passed out, we sort of reset the value of delta list. Okay, so this is a very high value, and then typically it is going to be updated as the deltas keep on coming. Okay, and we are always trying to make sure that what is the time that has elapsed. So millis is going to give you the current time in terms of milliseconds, and minus last cal is basically the time the system was calibrated last time, right? So whenever we do this update, we also keep track of the time. Okay, and if delta is of course less than this delta, we update the value of. So this is how you find out minimum anyway, right? So we are keeping track of or like maintain delta list, right, and update if necessary. Okay, and at the end of the day, we are reporting delta minus list delta. Okay, and now this is a very simple heuristic that we see now, and we will see how this performs much better than what we saw earlier, right? There is of course still some noise, but that could be smoothed out, but now it is much more responsive, right? Whenever you touch it, you can detect the touch. Okay, so this becomes way better than what we saw earlier, just by using the simple metric that we had, or not using the this new metric, right, or the simple metric that we had, and also not having the loop, right? So the loop sort of is important here. That helps to weed out a lot of noise, as you will see, and also improves the sensitivity of the system. Okay, so now we have implemented a very simple touch sensor. It's like an on-off switch. It's I would say a binary sort of a touch sensor, where we could simply detect a touch event, right, whether a touch has taken place or not. Okay, so this is a simple activity that you can try out. What I did was, it's the same sort of circuitry that we had. So the electrode is replaced by this bowl, right, where I kept some water. So this is like simple water, right, and the circuit is the same, right? The This is our sensing circuit, and we have an additional circuit to detect an event, right? If the event is detected, of course I use some kind of a threshold, and if the event is detected whenever I touch the water, it is going to sound an alarm, right? So just for fun, as a fun exercise, you can try to do something like this, and I'm going to show you. So this is the same code that I have shown earlier. Additional thing that I have was threshold. The threshold was hard coded, and if the value exceeds the threshold, it is going to sound an alarm and glow this LED, right? So this is, if you do it from scratch, it will help you go through all the concepts that was covered till now, right, to implement a simple touch sensing circuit, as well as the firmware, right? So this is the firmware that we developed in class, and you could see it in action. Okay, so I tried many variations, right? You can. So I'm not touching the metal per se, as you are seeing that I'm simply touching the water, right? And this is not going to introduce any capacitance, right? So this is a complete insulator. Okay, and whenever I'm putting my finger, right, so this is what is happening, right? So as you can see, we have the RC circuit here. So this is our high resistance, and we are doing all these RC measurements here. There was reference pin and the sensing pin. Okay, and this is a simple thing, right? Whenever there is a high value of the delta minus delta list that is detected, you can say there is a touch event, and then you can play a tune through a buzzer, or you can turn on an LED. So these are all connected to your digital input output pins, right? So if you just put a value of 1 in your some GPIO pin, it is going to momentarily switch on the LED. You can put a delay. It's very much like the blink program that we saw in the initial classes. Okay. Okay. So any question regarding this demo or in general, because we are now going to look at a little bit more complicated scenarios than the simple touch sensing, just the binary one, right? Whether it's an off-on switch, we are going to do something more than that. So if you have any questions till now regarding the implementation or something with the demo, you can ask, right? If not, I'll proceed. Okay. So now, what you can, the other things you can do is, as I was keeping on telling you, that the capacitance is also a function of the object or the material, right? That is touching the system or the sensing pin. So you could be touching the a pin, but through some kind of an object, right? Maybe you are holding something in your hand, and you are using that particular object to touch the pin, right? We can convert all these things into very useful practical applications, right? And what you can do is that we can do this small exercise of trying to classify the objects or the materials based on the value of your sensing metric, right? As you understand that there will be a certain variation of this value based on the object of the material, and you could use them for fingerprinting, right? You can use that as like label data, right, for different materials that you are using, and try to create a distribution of that, right? So for different types of objects and materials, the distribution of the sensing metrics can be learned or fingerprinted, and the prediction can be made based on some maximum likelihood estimates, right? So if you have a finite dictionary of the objects that you are considering, right, you can have a fingerprint of them already built up, right? And whenever that particular object is being touched or brought in the vicinity of the system, you can say, oh, this is the particular object, right? So to give you an example, I have this figure, right? So whether it's water, it's like a cloth, it's a book, or like an apple or banana, right? So all of them will have very distinctively different fingerprints, right? So if this is connected to the electrode or pin sense, whatever we call it, right, and somebody comes and touches that particular object, be it a book or a banana, right? So they will have these two different distributions for the sensing metric, right? And whenever you start receiving the value of your sensing metric on touch, because you are always doing this touch sensing operation, so based on the value of your sensing metric, you can see which distribution it is most likely to go to, right? So this is like a D1 for representing the distribution for banana, D2, D3, and so on, right? D4 and D5. So let us say you get a new sample and you try to see out of D1 through D5, which one has the maximum likelihood for that particular sample, and then you can conclude, right, using this simple algorithm, that what kind of material was actually brought in, right? How was the electrode touched through what kind of an object? So this is an interesting thing. Even if you try it out with two different objects, you can see this thing in action. Okay, so one of the suggestion is to try this out, because if you have the circuit built up that I have shown in the last slide, right, in the last video, you can also replace that bowl of water by this kind of objects. Okay, and try to see, try to appreciate the different distributions that you can get. Okay.
Hello, sir.
Yes.
Sir, for different material, almost the same. It looks like same only, no? Like even banana and apple value will be approximately the same only, no? How we can?
No, value will not be will not be exactly same. There will be some difference that you can notice, because the capacitance that will be brought in is dependent on the material inside it, right? It could be containing more water, it could be containing less water, it could be larger in size, smaller in size. So based on that, the value of capacitance will also be changed.
Okay, but in the some of if the water having lot of water and if
Less water, yeah.
yeah for considering that banana and apple, some
Mhm.
of the places we are touching like 2 fingers or 3 fingers, then approximately the value will come same, no?
No, it depends on, you can deliberately try to get one banana and one one apple, right, such that your sensing matrix becomes the same, right? But it's not a common case where you have like two different kinds of materials which is going to give you the same value of capacitance, right? So even if you touch 3 fingers or 2 fingers, there will be certain variation. So this is an activity meant for you to try out, right? So it's not going to give you 100% accuracy, but for different, very widely different objects, you will actually come across different values, right? And then you can tune the value to make your prediction better. Okay.
Okay sir, thank you sir.
So this is actually like you can look at a paper like this, right, where they made the electrode much more elaborate, right, where they were putting the object was some kind of a, they call it interactive fabric, as you see in the picture. So there they actually aligned the electrode on top of a cloth, right? So they nicely cut this thing out. As you can see, on top of the cloth they have put this electrode, and they have connected this to the sensing pin, right? So this is like P sense. And as you can nicely see, right, which portion of the cloth had what kind of a thing. Now they can look at each individual electrode, right? So they are now able to track a grapefruit here, uh, as you are seeing here, an avocado here, and a kiwi here, right? So they are not simply looking at a generic touch, right? So all of them you can touch, right? But there is a certain gradation of the value which is going to help you classify that particular thing, right? So in this case, they are trying to look at watered versus unwatered plant, right? So if the soil has a lot of moisture content, you are definitely going to see a different value of capacitance. So if you are really interested, you can, that's why I put a screenshot of this paper, right? It's very recently published, and lots of interesting things are being done. As you see, there is also a lot of interest from industry side. So Microsoft Research is doing a lot of work like this. Okay. So particularly in the human computer interface conferences like CHI or UIST, UBComp, you will see a lot of variations of touch sensing that is being applied to such scenarios, right? So this becomes a very cheap system. You don't have to spend a lot of money buying components and equipments. Uh, just using the processing algorithm smarter, the sensing metric can be made smarter, and they are sort of able to detect a lot of these different things, right? So I cannot cover this entire thing in this class, right, because it will take too long. But you are encouraged to look at these papers if somebody feels that interested. Okay, so material identification could be potentially done using this concept of capacitive sensing. Okay, so this is another example from the paper where they have actually found out differences between so many types of different things. And as you can see on the right hand side, the spectrum of the different items they have considered, right, starting from this AirPods case or lipstick to all the way to like glass candle, empty water glass, and so on, right? Water glass filled with water, empty bowl, like all of them could be actually distinguished because they will have very different signatures, right, that will help you identify the material quite with a lot of like good accuracy. Okay. Okay, so again, please look at the paper, and you can see that this indeed works. Okay, so this is an example that I have showed you on the very fast class, right, where I was trying to interact with this set of switches, right. This is these are all aluminum foils, right, no other thing is present, and these are all serving as electrodes connected to a touch sensing IC. So touch sensing ICs are available which have ready-made touch sensing capabilities. You don't have to create all this circuit that we were showing earlier, and also don't have to write the firmware, right. So all of these things are implemented in hardware, and they are always going to give you some kind of a metric that this particular chip gives out, right. So many vendors will have such chips, right, ICs, and typically they will be interfaced through an I2C interface. Okay, and you will have several channels. So channel means each sensing pin will be a channel. So in this particular example, we are having a 12 channel capacitance sensor, right. So these are not very expensive. It will cost you like 100 rupees or 200 rupees at max, right. And they can be interfaced very easily to a microcontroller or like an Arduino using an I2C bus, right. And you can get all the values from these 12 different sensing pins, and all the sensing pins could be interfaced with 12 electrodes, okay, or 12 basically touch points, right. And you can choose one of them that you are interested in. So this example I showed you in the very first or second class, right, where I had this sort of a game implemented where I want to interact with some of the blocks that are being shown in a computer screen, right. So just by touching all these things, where I was trying to show you the divide between the real and the virtual world or the cyber world. So whenever I'm touching a particular electrode here, so that is being reflected on the screen, right. And this was a simple game where I have to immediately touch what the computer shows. In this case, the computer shows 2, so I have to immediately touch 2, right. So this is, and you can try to find out how much delay you are making in order to touch that particular electrode. Okay, so this is just like for fun, but the idea is that you can, without going through all these things, ready-made ICs are actually available, but currently the knowledge that you have is what goes inside and how can it be implemented completely in the software, right. So that idea also you have. Okay, and some microcontrollers will also have a capacitive touch sensing pin, right. So you always don't have to use an external IC. Some advanced microcontrollers, I know some of them in the STM32 family, they will have some pins that is capable of doing touch sensing. Okay, so that is something that I wanted to mention. Okay, and you can do something of this sort also, right. If you have this 12 channel capacitive sensor, you can form a grid like this, right, so that you have 6 in one direction and 6 in other direction, and whenever you touch one of these pins, right, one of this area, so both this and this will become activated to some extent, and you need to figure out some metric to figure that out, right. You have to figure out of all these 36 points in the grid which particular point was touched, right. There are like standard algorithms to do this, but you can also figure out your own. Okay, so you will read the sensing values from all of these 12 pins, right, continuously, and from those 12 values you have to figure out which particular portion in this grid was touched, right. So instead of having a 36 channel capacitance sensor, we are doing it with a 12 channel one, right, where we can do this crisscross of this electrodes or these strips, right, and based on the values that you are receiving on the microcontroller end, you can figure out an algorithm how to detect a particular touch point. Okay, so these are the things that can be done, right, and these are not very like complicated algorithms, but once the system is set up, you can use that to create a lot of different things like this, right, and this becomes like a very like sort of a DIY or like very cheap version of a touch screen, right? It does give you touch functionalities, and you can, like, for example, you can write very simple shapes on top of this, right? Let's say you are drawing some number, right? Let's say you want to draw something like in form of an 8, right? And you can use standard OCR algorithms to figure out that what sort of a figure was drawn. Okay, so if you write like an 8, so you have to basically see what are the grid points that were actually touched, and that could be fed on to some let's say some ML algorithm, right? Very simple one, which is going to tell you, okay, the thing that you tried to draw on that screen was 8. Okay, so you can do a lot of fancy things on the algorithmic side. Okay? But yeah, with a very simple hardware like this, right? The hardware doesn't cost you more than 100 rupees. Okay, so we'll come back to our filtering heuristic, right? So why we call filtering was because we are using the same heuristic for removing the noise, right? And the way we were using delta minus delta list. So this actually also helps us to implement a low pass filter, right? Very simple one, but it does get rid of some of the high frequency things and some of the noise in the way, because we are using sort of an average, right? Or we are basically trying to sum up all these things over a smaller over kind of a period of time defined by our window. So based on how many samples we are taking, so this is not only getting rid of the noise, but it's also going to improve the sensitivity of the system, right? The detection will be much slower, because if you are using, let's say, 200 samples versus if you are using 10 samples, the interactivity could reduce a bit, right? But at the same time, it is going to give you much less noise in the system, and also it will improve the sensitivity of the system. Okay, and in this case, as you will figure out, as we'll actually show you, that instead of even touching the particular electrode, even it is going to show some response for proximity, right? Instead of touching the electrode, even if you bring your hand in front of the electrode or in close proximity of the electrode, it can start responding. Okay, so that is a very interesting observation that you will make, right? So instead of doing touch sensing, it is also going to, the same circuit, the same code is also going to be doing some kind of a proximity sensing. Okay, so this will be very nice, because now people don't have to touch the particular button, right? Even if he brings his hand nearby the button, we can still detect that. Okay, so this will be pretty much applicable in places, in public places, right, where everybody touches the same button, and then you have to use your like hand sanitizer and wash your hand and so on. So all these issues goes away, right? Let's say in an elevator, right, where everybody is touching the same button, the what floor you are going to go, right? And that could be replaced by capacitive touch sensors, right, where you can simply bring your finger near that particular button, and then this is going to trigger the switch, right? Of course, it's not going to work in a very crowded elevator, right, because that is going to turn on all the buttons, right? So there is some engineering that has to go on in there about how to design the sort of an optimal proximity sensor, right? It's not going to be too sensitive, right, and it is not going to be very less sensitive, right? It can work without touching the switches. Okay, so we'll see this in action. So we are going from touch towards proximity for the time being, right? Where touch, as I said, you have to physically touch the sensing pin, and in case of proximity, you can just keep your hand near the electrode, right? And what is the distance of your hand to the electrode, right? What kind of capacitance that particular object or your hand which is in close proximity to the electrode can bring. So all these things are sort of interrelated, right? What is the distance here? Okay, what is the maximum distance rather? What are the properties of this hand or the object that we are bringing in proximity to the electrode, and what is the properties of the electrode itself, right? As you saw in the last paper that we were discussing for material identification, you could see that the entire electrode was sort of laid in form of a strip on top of the fabric, right? So the electrode could take any sort of shape. Okay, so that could also improve the sensitivity of the detection. Okay, so one example could be, we can use a simple plate kind of a thing, right? As an example, I'll show you this, right? Instead of just the dangling pin, we can connect that pin to some kind of a plate which has some larger area, right? It's a two-dimensional like an aluminum foil which will have much greater area than the dangling pin, right? It is going to improve the sensitivity to a higher extent. Okay, so this will help you in increasing the sensitivity. And a very simple example of this is on the left hand side picture, right? You can take a simple cardboard, and the cardboard, you can wrap that cardboard with an aluminum foil, right? And that will also make the surface area of the aluminum foil or the electrode larger, right? And then I had like two pins jutting out. You can ignore one of them. So this was just for improving the sensitivity or doing some other experiments, right? For now, you can simply assume that this is one electrode and you have just one pin connected, right? So this is basically going to the microcontroller, and this is the P sense. Okay. And you are basically this entire thing is your electrode, and you can touch at any point of within this electrode. Okay. So not only that, what we are also going to show you is that you don't have to really touch this particular electrode. You can even bring your hand nearby, and that is also something that could be detected, right, without any touch. Okay, so what is happening is this column, right, in between your hand and the electrode. So this is storing some form of charge, right? So this is your sort of a virtual capacitor that you are introducing to the system, right? Which we sort of discussed in like 2 or 3 classes back when we tried to understand the model of this capacitive sensing. Okay, the circuit model. So this is one more thing that we discussed about the low pass filter with the code, right? And this is the number of samples here, right? So 10 or 20 or 100 or 200, right? All of these refers to the number of samples, right? Let me write it down. So this is the number of samples that we are using in our filtering heuristic. Okay, so as you are seeing, more the number of samples, better will be the detection accuracy. And what we are doing here is you have the simple sensing circuit implemented on this breadboard, and on the right hand side we have the Arduino, and you are seeing what is being sent out from the Arduino to the PC. So this is the output. I'm basically seeing the serial output, and this is our electrode. Okay, so this is our electrode now, and we have a small wire that is connected here, which goes all the way to the sensing pin. Okay, and what I am doing with my hand is like not always touching it, but I am trying to make some movements without touching the electrode. Okay, so this is more of a proximity sensing. And as you can see, the performance of these different algorithms, right? If we bump up the value of samples, right, in your heuristic, the way we can detect the this periodic fashion by which I am moving my hand is much more stark, right? So if you see this one, it really gets rid of the high frequencies. So all we are left with is basically what happens because of the movement of my hand, right? If you look at this very carefully, you can look at what frequency I was moving my hand, right? And if you see the one with 10 samples or 20 samples, we can barely detect anything, right? Mind that we are not touching the electrode per se. It's just based on proximity sensing, very similar to the way we were using the IR sensor, right? When we were putting our hand very near to the IR sensor, we could detect that this kind of thing, right? But as you see, this solution is way more cheaper than that. We don't have any IR sensor or any other complex sensor for that matter, right? So Only thing that we have is a high resistor, right? And rest of it is sort of a cardboard and an aluminum foil wrapped around it, right? So we still have a proximity sensor now, and just by improving the heuristic, right, that we built, and improving the low pass filter by having more samples in it, we could have a very nice idea about the periodic motion that we were doing with our hand without touching the electrode. Okay, so that is very important, right? Maybe if you are touching the electrode and untouching it, even with 10 samples you could get some kind of a pattern like this, right? Because you are physically touching. The problem becomes more sort of a complicated, or like I would say not complicated, but the SNR of the signal becomes very low when you are trying to do all this proximity detection using this circuit. Okay, so again, if you have built the circuit, this is something that even you can try out. Okay, and just get convinced yourself that this indeed works. Okay, so the next thing is proximity detection is still the same thing. We are using this value of filter and so on, but as you will see that at the same time we can do some kind of gestures that that could be detected. Okay, so if you sort of analyze this signal, right, that is you are seeing on the right hand side, this sort of signals could be converted to some kind of a actuation that you want to do on the microcontroller end, right? So this is what happens when you touch. The value bumps up really high, right? So everything you do with your hand, right, some of the learning that could go on with these time domain signals, right, could be used to express a certain gesture, right? Here I'm rotating the hand, or like using two hands and so on. So all of this could be learned, right, and in form of a model. You can store this model and then based on whatever gesture you do in on top of this plate, right, it could actually be converted uh, to some kind of an actuation, right? You could turn on or dim a light, or maybe like if you want to do some kind of smart home automation, right, you can use one gesture for turning on the fan, you can use one gesture for turning on or turning off the light and so on. Okay, so all these things could be classified, I would say. Okay, because these are basically time series data that you are getting. You can look at the frequency domain features, you can look at the spectrogram, right, the way I sort of taught you in the last class, where I was looking at the spectrogram of the IR sensing data, or the PPG data, right? Even this could be converted into a spectrogram, and then you can try to learn that gesture from the spectrogram, and based on the classification of the gesture, you can try out one of these activities, or like actuations, right? You can turn on the fan, light, TV, and so on. Okay, so this is another angle that I am throwing you, that could be taken up, right? If you have interest in this kind of systems, you can explore all these things more, right? And the good part is that you don't have to spend a lot of money in order to create the system or investigate such systems, right? These are really cheap. Okay, and all the things that you have to do is how smart algorithm you can design in order to digest this time domain data and convert that into some kind of useful model. Okay, so now we have a pretty good idea about the touch, right? At least detection of the touch, as well as proximity sensing using the same circuit. Now we are sort of going one way deeper, like one level deeper, and trying to see whether we can locate the touch, right? So this is something that often happens, where we will not have a lot of electrodes, right? If you have a lot of electrodes, based on which electrode you touch, your touch would be localized, right? But if we have lesser number of electrodes, what should we do, right? Which often happens in case of a slider, right? All of you have seen sliders like this, right? You will have sliders in computer GUIs, right? But on physical interfaces, let's say you want to have this kind of a slider, right, on a table. Can you have this sort of slider which could be slided, and based on that you can dim a light, right? In your reading table, you might have a virtual slider like this, right? That will be great, right? Without having any mechanical knob or any other switch, you simply swipe your hand on top of your reading table. That is going to adjust the brightness of your light. So till now, the touch detection gave us on-off buttons, that is a binary input. Now the touch belt sliders is going to allow for a graduated input, right? Where you can have multiple levels of, let's say, brightness of the light. Okay, and what you are going to do is simply uh, swipe your finger on top of that particular surface. Okay, so how we can do it is that we can simply connect the pin sense, right? And it can either touch the particular surface or it can be in close proximity of that pin sense electrode. And we can simply calibrate the system in the following way, right? We can have a sensing metric designed and for this pin sense 1, and we can have a d min, which is the minimum distance, and d max, and we can calibrate the same thing like this, right? So with distance, the sensing metric is going to come down or go up based on what your metric is, right? But it is going to have a monotonous pattern. Okay, so but the problem with this, right, is again a calibration issue, right? Because based on how you are touching it or who is like touching the surface, right? Or whether you are touching in a particular way with 2 fingers or your entire or just your thumb, right? Things might change, right? So it could basically become something like this, right? Which is basically going to make the distance estimation a little bit tougher. Okay, so what could be a good solution? A simple solution that could also help you in self calibration is, instead of having just a single pin, you can have 2 pins on 2 ends or 2 electrodes on 2 ends. Okay, so if you have this particular pin, that is also another sensing pin which is connected to the other end of the sensing strip or the sensing area, then you can realize a graph like this, right? Where if you are diminishing the value of the sensing metric 1, which is coming out of pin 1, the other one starts gaining, right? Once you go to the vicinity of the other side or the other electrode, that is going to pick up and this is going to go down. So based on this particular data, you can always self calibrate the system, right? So whatever object or whatever material you are going to use for the touch, these 2 graphs is going to look the same. It is just going to be an exact opposite, right? And what you can use, like one simple heuristic that you can use, is simply difference of these 2, right? It is, there will be some value in between where both of them might have a very similar value of the sensing metric, which is going to give you like a 0, right? This could be like delta 1 and this is delta 2, and what we are plotting is like delta 1 minus delta 2, okay, or delta 2 minus delta 1, whatever be this, right? So in that case, you can nicely have something which can be used to track an approximate distance for the slider. Okay, and you don't have to really look at like very fine-grained resolution, right? Most of these cases will have, let's say, for any practical system that we are talking about, let's say we want to dim a light bulb, right? You don't need something which has like 30-40 levels, right? Maybe 4 or 5 levels could be good enough, right? And then you can simply use different thresholds, right, where you can use this for this graduated input. Okay, if and then this could be self calibrated. That is the good thing, right? Because you have the electrodes attached on both ends, so you know some kind of a mean and a max, right? And then you can uniformly divide that, right? Or if you have more knowledge about how the capacitance changes as a function of the distance, or the metric changes as a function of distance, you can make a better design. Okay, so you can also do it for touch-free sliders. You can just simply mimic a sliding gesture in the air in the proximity of the electrodes. That could also work theoretically. It's just that you have to tune the system for detecting, for doing touch-free interaction. Okay, so this is one example where you can do this 1D touch localization, and a common example is a slider, which is a pretty common HCI interface. Okay, which is something you can realize using physical objects. Okay. And there is one more thing I want to show you. This is something I also covered in the last year's class, was using the entire small plant as an electrode, right? This electrode here of the sensing circuit is connected to this plant's trunk. Okay. And however you interact with the trunk, right, of the small plant, is going to show up in the sensing metric. Okay, so if I also connected this system with a buzzer, right? So the sound could be a little bit awkward of this buzzer. It's just that however you touch the particular area of the plant, or whatever is your pressure, right, based on that I am changing the frequency of the buzzer, right? So we can see it now, right? So just the sound is bumped up, so there's a lot of noise here. So this is proximity. I did not even touch. So you can clearly see there is a lot of space in between my hand, and so this is for touching. So this was a light touch. So as you will see here, the intensity of the touch or the way we are touching could all be detected. So it's a little bit longer. So it's a pinch. So all of these things I am doing, right, could be encoded in form of a model, right? You can, what kind of action you are doing with the electrode, that could be detected in real time. So the sound is a little bit higher, but so you can see that the changing pressure could be so clearly identified. Okay, right? So as you will see that you see the system, right? So this is just, we have a single wire that goes or runs into the soil, right? I put it in a glass, in this paper glass, right? So only thing that we have here is one wire that is jutting out of the system and goes to the sensing pin of the microcontroller, right? And the other part is the buzzer part, where I simply convert the sensing metric to some kind of a frequency that I play through the buzzer. Okay, so the circuit is as simple and the same thing, right? And as you could see that there is a lot of scope here, right? Based on my changing touch pressure, right? That could itself trigger some different kind of a different kind of an action, right? If you are pressing the electrode too hard, maybe I want to make the light glow brighter, right? If you are, instead of a slider, you can even do it using a simple touch pressure. Okay, this can also be detected. Okay, so what I'm trying to get at, right, is the different kind of things that you can do with this very simple circuit. Okay, that's the reason I sort of introduced this to you, because right after going through the capacitive touch screen, we could have just gone to a different topic, but it's kind of building a capacitive sensing system from scratch, right, and using a simple microcontroller. And as you can see, you can start interacting with physical objects that you see around, right? So the point of showing this plant, right, is that you can connect these electrodes to things that you see around as we see around us, right? So some of the projects that I have given was motivated by this kind of things, right? Let's say you sit on a chair, or somebody doesn't sit on a chair, right? Whether there are any capacitive differences that you bring to the system, and you can immediately detect that somebody has sat on the chair. Okay, so if you connect the electrode to let's say the chair, can we detect whether can we classify which person out of the 5 people that stays in a house, which person has sat on the chair, right? Can we build a simple classifier based on this data? Okay, so this could be very interesting things to look at and think about it, right? Without using a camera, without using any sophisticated sensors, we are trying to do this. Okay, so there is a little bit this advanced extension to what we have already seen, right? For this concept called swept frequency capacitive sensing. So if you try to understand, this is a nice sort of a metric that we can use for doing the same capacitive sensing, but a little bit more involved in the conceptual side. I'll try to explain it in very simple terms, right? And it is just for the sake of completeness I want to mention this, right? This is a big topic, and there are lots of papers that are being written on this particular concept, right? For more than a decade right now. So I'll share you one or two key papers which has been published, which basically describes this principle. And then if you again feel interested, or you are trying to do projects in similar lines, you can explore this in details. Okay, so whatever 15-20 minutes we have, I am just going to cover the basics of it, right? It is not possible, like we can have an entire semester long course on touch sensing, right? But we are just taking 4 or 5 classes out of this course to explain you the basic pointers or some fundamentals in this direction. Okay, so what does this thing mean, right? What is the swept frequency? So as you understand that we have two sides of the system. One is the touch sensor that we are talking about, and on the right hand side we have the environment, or the touch, or the human being, or the material that is used for touching. Okay, and on the left hand side we have the touch sensor, which is nothing but a combination of these elements, right? As we have seen earlier, I was just bringing up the capacitance, but again you could have some inductance or some capacitance, some resistance that could be used to represent the touch sensor. Okay, and all of you know is that if you try to excite this system using different frequencies, right? Not one frequency, but different sets of frequencies. For one, given the characteristics of the sensor, what are the values of R, what is the value of L and C, you are going to see some kind of a resonant frequency, right? Where you will have all these different frequency components, right? And for one value of frequency, the amplitude of the system is going to be very, very high, right? Where the peak amplitude at what frequency it is happening, we are calling it the resonant frequency. Okay, and we are passing all sorts of frequencies to the system. Let's say from f0 to or some fn, right? Different frequencies we are trying to introduce. So this is a sort of a lower frequency, and we are sort of increasing the frequency with time, and here this is a high frequency. Okay, so if we can input such a frequency to the touch sensor, right, based on the values of this RLC that are already there in the sensor, we are going to get a certain FO output frequency where this value will be maximized. Okay, so this is the resonant condition, and this could be given by 1 by 2 pi root over of LC that you have already studied, I think, in high school. Okay, in the 12th grade, you have probably studied this. Okay, this is all this LC oscillation and so on. Right now, what we are doing is that everything remains the same, right? What we are introducing is a touch object, right, which again has a series of this inductors and capacitors that is being introduced to the touch sensing system. Okay, so now these values of the effective values, if you redraw this entire circuit, the effective values of L and C would be changed, right? And because of these values, change in these values, the resonant frequency of the system is going to change. Okay, so now because of the touch that has taken place, right, we are not going to have the same value or of the different frequency components. So maybe this value is going to be shifted here, and this is the FT, or the resonant frequency after touching, right, the system. So now instead of F, we are going to have FT, and we are mostly interested about this delta F. right? So what is the base condition here? The base condition is F0 or F0, right, when there was no touch present in the system, right? And whenever there is a touch by a certain foreign object, right, which is coming from the environment, we are going to introduce the changed values of L and C and R, which is going to change the value of the resonant frequency, right? And what we are measuring is how much it has changed. Let's say it was F0 earlier, F0 or F0, and now it is like Ft. So we are trying to look at this delta F, okay? And this delta F is a function of the object that you are using, right? So that is one more way of leveraging these resonant frequencies to detect what kind of material, or it is very effective not only for detecting touch but also the identify the material, right? Try to do fine grained gesture recognition, right? You are basically getting a lot of rich information using this particular approach. Okay, so this is one more approach that I wanted to quickly discuss. Okay, so is there any like is this overall thing clear, right? So I'm not going to expect that you will understand the nitty-gritty details right now. I'll share a paper about this where you can understand what is going on, the internals. But what you can see is that we are introducing a frequency, and we call it swept frequency because we are changing the value, we are sweeping the value of frequency from some F0 to Fn, right? And after that, we are receiving the output response of the system. Okay, so there is a base response where there is no foreign object that is introduced to the sensing circuit, and there is another case where I am introducing a touch object to the electrode. So this is basically the electrode. Okay, so after introducing this, right, there is a delta F, that is an additional shift in the resonant frequency, and this delta F could be something that could be used for fingerprinting the object. Okay, so a paper based on this particular idea, right, is this touch paper, right? It is enhancing the touch interaction on human screens, liquids, and everyday objects. It's a recent paper that you can take a look at. So the swept frequency capacitive sensing concept is used here, and they have a very nice demonstration of what you can do using this particular concept, right? I am going to show some examples from the paper. Let's say they have this electrode connected to a door knob, right? And they want to detect what happens when you touch the door knob in different ways, right? So they have these different classes they wanted to classify. The black one is for like no touch, right? So if you see the black plot of what happens when there is no touch versus what happens when you are grasping it with like the entire hand, right? So in this case, right here, so this is the orange plot. So you can very distinctively see, right, all these different gestures on the door knob are creating different signatures in the in this frequency, right? There is a definite value, there is a definite shift in the resonant frequency, right? Whatever you are seeing here, whatever you are seeing here, whatever you are seeing, there are slight differences, right? And it could be well detected. Okay. Another example is this, right, where you have this table, and within the table you are this is connected to the electrode, and there is some person who is sitting in front of the table, and we are trying to get the gesture she is making, right, starting from the time when the person is not present, and then looking at all the things that she is doing with her hand. She's touching the table with one hand, she's touching the table with two hands, she's touching with one elbow, and so on. So all these different things, all the gestures she is making could be all captured by this SFCS system, right? Which could be pretty difficult to do with the type of touch sensing that we were doing earlier. Okay, so anyway, I'll take a little bit extra time today to finish this off, right? So people who have other classes, you can leave, but I'll since we are recording this entire lecture, I'll finish this entire thing and then like finish up the class, right? So that we have this complete picture of the touch sensing done today. Okay. So now the problem is that if you are looking at the touch paper, right, the hardware that they were using was very like really fancy. So this was trying to create sine waves. So if you see this example where the way we were trying to generate these frequencies, right, this is sort of sine waves we are introducing to the system with increasing frequency values, right. Initially it will have a low frequency and slowly we are bumping up the frequency. Okay, so it's very similar to something we call a chart sort of a signal, right. Initially with the time the value of the frequency is, let's say, linearly increasing. Okay, so how do you do it with a cheap microcontroller? Our Arduino kind of a system cannot produce sine waves, right? So we have to somehow come up with a hack to do all these things, and there is a nice paper which describes this, and I'm also going to show you how you can do it real cheap, right? So you can actually implement this system without using a fancy digital synthesizer, right? That the touch people have used. Okay, so while Arduino is capable of generating frequencies in this range from 1 kilohertz to 3.5 megahertz, the signal is a square wave, and there will be all sorts of harmonic frequency components that will sort of tamper the reading that you are getting from the system. It will be not as clean as we show in the previous plot, right? If you see, these are like really, I would say, clean signatures, right? But if you are trying to do this with just using a square wave and increasing the frequency of that particular, the duty cycle, right? So this is not going to behave in the same way. Okay, so simply using the signal with the circuit described in the touch paper, if you look at the paper, they are describing the details, will result in a highly messy frequency graph due to the harmonics from the square wave. So you will see this sharp sort of changes, right? So this is going to result in a lot of harmonics, and the way to counter this problem is to basically filter out all those unwanted harmonics using a LC circuit. Okay, so I'm not expecting you to know all the details here, right? Just to introduce to this concept, I am going to cover this filtering aspect. But if you are not familiar with all these RLC circuits or the network analysis, I'm sort of not expecting you to at least understand this part of the code or this part of the circuit where how you are removing the harmonics. Okay, the rest could be used as a black box, and then you can do all the sensing operations that we are describing, right? All the classification or all the inferences that we are making from the system is still applicable. Okay, so this is a simple circuit like this. People who are from the E department, they'll be probably be more familiar with this, right? How we are trying to filter out the harmonics, and we are simply borrowing this circuit from the paper, right? You can take a look at the paper. They will have a nice explanation why they are doing it, and we simply convert this particular circuit on the right hand side, right? So we have 4 electrodes. One is for the ground, right? We are connecting all of these things to the ground. So this is mapping to R1, this is L1, this is the C2 in the figure, this is the object or X2, this is the diode, right? This is R2, this is the capacitor C1, and this is the resistor R3. Okay, so and this is pin sense, this is going to the microcontroller, right? And this is the object, and this is where we are using it as the reference pin for sending the frequency sweep, right? So this will be used for introducing the swept frequency to the system. Okay, and we are going to look at the response from here. So we have simply set up this circuit on a breadboard. That's why I drew it in this kind of a weird way, right? So just to map it directly onto the breadboard, and this is the final picture. Again, the cost of these components is probably not going to exceed 20-30 rupees, right? There is nothing fancy here. There's just one inductor. This is the inductor, right? And you have like these 3 resistors. This is the 10 kilo ohm, this is the 3.3 kilo ohm, and this is the 1 mega ohm resistor, right? And then you have this diode, and you are measuring the voltage here, okay, after the across the diode here. So this is where you are measuring the voltage that goes to P sense. Okay, this is going to the microcontroller pin, and here you are actually having the touch. Okay, so this X1 or the object, this maps to this part of the figure, right? Where this is the electrode that you can use it for touching or connecting to some kind of an elaborate electrode. Okay, so this is the firmware, right? I'm going to share the slides with you. You can take a look at it, right? How we are generating these frequencies. So we are generating the frequency using a timer. Okay, so I am not going into the details of the timer now, but this timer could be, if you look at the Atmega manual, you can see that the timer could be loaded with a certain value, and it is going to create a certain frequency, right? So the timer could operate at a certain frequency, right? And this could be depending on the value that you load onto the timer, so it is going to create a different kind of a square wave with a certain frequency. Okay, and this could all be done using this timer that we already have in Arduino. Okay, so philosophically, you can understand the code is that we are basically setting up the timer as a frequency generator, right? And we are basically having one pin that is going to be outputting this particular frequency that is going to be fed to the circuit. Okay, and then we are trying to store the result, right, of the response, right? How many frequency components we are using. So here we are using, let's say, 160 different frequency components, right? In the frequency sweep that we are going to present to the system. So how many, so starting from a very low one to a very high one, how many different frequency components we are presenting to the system. So this is discrete here. So we are basically having 160 different frequency components that we are going to feed to the system. And now there is the loop part of the code where we are continuously increasing the value of the frequencies. We start from d is equal to 0 and d goes all the way to 160. And with all this particular value of d, we are configuring the timer, feeding that particular frequency to the circuit, and then recording the response in results. Okay. So this part will be pretty clear, right? This is how you basically reload the frequency in a timer, and this is very well explained in the manual. How do you use the timer or the counter as a frequency generator? Okay, so if you still have confusions, we can go over it, or I can redirect you to the part of the manual that you need to look at. Okay, this is all. This is going back to the Atmega microcontroller manual that we shared in the first couple of classes. Okay, so what we have now is this results array, and this results array will have this particular offset d, and we'll have 160 such d's. Okay, 160 such values of results, right? Where we were recording the response. Okay, some of them will be low, some of them will be high, and so if you see result array like this, let's say this is results, right? And this will be some for some d. So here this will be d is equal to, let's say, 0, d is equal to 1, all the way to d is equal to 159 if you have 160 components, right? And what we are interested in doing is plotting this value, and one of this value will be high because this certain value of for a certain value of d, this will be your resonant frequency. Okay, so that's all, right? If we just want to know what is the value of your resonant frequency, we can simply do that. Okay, and this is a demo that I'm going to show you, and which is basically showing you the resonant frequency when the system does not have a connected electrode. So this is dangling now. So if you see, this is the same circuit that we have shown earlier. So this is the dangling electrode, and what is the response that we have across from 0 to 159? You see that the frequency that it peaks is here. Okay, and now I will show you that what happens, right? You can bring a change to this particular behavior by connecting the electrode or making certain gestures. Okay, so now what I will do is I'll connect this electrode, and since I'm holding that electrode in my hand, you can see a stark difference in the values of the frequency components. Okay, so this again can be used for fingerprinting the system. Okay, now I'm going to use this entire plate electrode that I've shown you, the cardboard that is wrapped in the aluminum foil, and connecting this particular electrode to the system. Now you can see you are seeing some sort of high values here. Okay, and once I keep my hand on top of this electrode, I see a different signature, and there is a lot of noise that you have to work with. So this is a very rudimentary example of or a demonstration of this swept frequency capacitive sensing that I just wanted to mention, right, to make this thing on capacitive sensing complete. Okay, so this circuit that I have mentioned is just for implementing it on a using this Arduino system, right, or like a microcontroller based system where I do not have sine wave generator, right, or a generator of this frequency sweeping thing, right. So that's the reason we need this, but you can simply take it as a black box and you can concentrate on the values, right, that you are getting. So on this array, right, so this is the results array, right, which is storing the responses for different frequency components, right, and this was being generated by our timer. Okay, so this could be learned again. Okay, if you want to do some sort of advanced sensing, the values of this capacitance and the inductor could be changed. It could be tuned based on how you want to do the sensing or how sensitive you want to make this system. And then suppose you want to make certain gestures, let's say you want to tap this particular surface, right, or you want to swipe this surface, right, all of these things could be picked up, potentially picked up, if you want to make this particular algorithm smarter, right. So this will be an input to your algorithm, right, and your output will be the gesture class. Okay, so this will pretty much use some kind of an ML model, okay, where you want to learn these arrays, right, right, to make the prediction better. Okay, so this will pretty much end up what I had to discuss about for capacitive touch sensing. And if you have questions, we can discuss that now or in the next class after the holiday is over, right. There are like a couple of breaks, right, and after that, after the puja is over, we will resume the class, and I want to focus on localization, right. That is one of the main areas that will be covered in the